Memorizers. Welcome to Chapter 8. We're going to start trig now. So we'll take our time and review all the geometry aspects of right triangle trigonometry before we get into the real Algebra 2 aspects of using trig. Okay? We'll start by reviewing right triangles and the Pythagorean theorem. We will get into Pythagorean triples and we'll spend a little bit of time there. Then our awesome trigonometric functions, sine, cosine, and tangent. So we'll look at those ratios and how they compare in right triangles. We will stop and review, and then we'll actually apply right triangle trigonometric ratios of sine, cosine, and tangent to finding missing sides in right triangles, finding missing angles in right triangles, looking at problems where we determine should we use the Pythagorean theorem to solve or should we use a trigonometric ratio to solve? And then we'll apply them to word problems. So the bigger application pieces, exam and review. Okay? So there we are. Let's get into trig. My fave. Here's lesson 1, right? Right triangles and Pythagorean theorem. Save my blank papers for you peeps. So, what's a right triangle? Well, a triangle is a three-sided, two-dimensional shape. It has 3 sides, 3 angles, and all of the angles in a triangle add up to 180 degrees. If you have a right triangle, it means one of your 3 angles has to be 90 degrees. And then that leaves the other 90 degrees of the triangle to be divided between 2 other angles. Okay, so since all triangles have to add up to 180 degrees, the other 2 angles are easier to find their measurements with when you know that one of your angles is 90 degrees. And we indicate a 90-degree angle with this little box at the angle. Okay, so each of these is a right triangle because it has that little box. Okay, so if that one angle is 90 degrees, then the other 2 angles add up to 90 degrees, something we call complementary angles. You probably remember all of this from geometry. Okay, so those complementary angles, the other 2 angles besides the 90-degree angle, those are going to be the angles that we kind of look at and question when it comes to our trigonometry ratios. Okay? The one thing we always know, and this is getting ready to use the Pythagorean theorem, is that the side across from the right angle is the largest side in the triangle and is called the hypotenuse. Okay. So the side across from the largest angle is the largest side. The angles are in proportion to the sides they're across from. Okay, so the smallest angle is across from the smallest side. The largest angle is across from the largest side. So if you have a right triangle, then the largest angle has to be your right angle. And that's the nature of having only 3 sides and only 3 angles, and knowing one of them is 90 degrees, but they all have to add up to 180. Well, then that 90-degree one has to be the biggest one, and that's it. So here are all the hypotenuse sides because they are all across from the right angle. Okay? When it comes to the Pythagorean theorem, you know, the whole a squared plus b squared equals c squared thing that we all know and we all have memorized and we all always have, right? When it comes to this, a and b are your legs, which are those other sides in the right triangle, and c is your hypotenuse. So your hypotenuse is always that biggest side, and that's why the square of the biggest side is the same as adding the squares of the 2 other sides together. That's essentially what you have when you're looking at Pythagorean theorem. Okay? The Pythagorean theorem, this idea is just the proportionality of the sides in relation to knowing that you have a right angle and knowing that this side across from the right angle is the hypotenuse and the biggest side. Okay. So this is a proportionality that it's a really cool, naturally occurring thing that we can use to our advantage. And we do when we're applying this stuff. Okay. It just means that, like, if you know two sides in a right triangle, you can find the third by plugging into this equation. Okay. Plugging into this idea. It also means for any coordinate geometry stuff or in our future trig stuff that we'll be using, or like when figuring out the radius in a circle, you use the distance formula, which is all of the Pythagorean theorem figured out for one of these variables, c. Getting c alone, that's the distance formula. Okay. So that's why it's so neat how this works. Like in this case right here, I know 3 and 5 are my legs. What's the length of my hypotenuse? Okay. One of the cool things about this is it applies the idea of having a principal square root. I took the square root of both sides here. This should be plus and minus radical 34, right? I'm not going to have a negative length of a side. So that's when I don't have to add the negative to part of the radical. Okay. It's also where I realize that very, very infrequently am I going to be able to get all three sides as integers. Very infrequently. In fact, so infrequently that when it does occur, and I will go back to examples 1 and 2, I just want to say this first. When it does occur, we call it a Pythagorean triple, because these are the very few spots where all three of the sides in your right triangle are all integer values. Okay, this does not happen often at all. Now, there are a infinite number of Pythagorean triples possible. However, the most used are these 5 that I've listed here, and any multiples of these 5 that I've listed here. After that, the numbers start to get a little bit too big for our regular daily use trigonometric problems. Okay. So these aren't places where we're going to see stuff that's outside of the realm of these particular 5 Pythagorean triples that I've listed. Also included are multiples, like I said. So if you multiply 3, 4, and 5 all by the same value, that itself is also a Pythagorean triple. So 3 times 2 is 6, 4 times 2 is 8, and 5 times 2 is 10. So a 6, 8, 10 is also a Pythagorean triple. That just means that when plugged into the Pythagorean theorem, these all come out to be integer values. Okay, and they all have integer lengths of sides. And like we say, it's so infrequent that we have perfect squares that exist in just our regular groups of numbers, that a lot of times you're going to get a non-perfect square under the radical having an irrational number. Okay, we already know how to deal with those because we've had plenty of practice dealing with irrational numbers and just non-perfect squares under the radical and simplifying those. So because we've all had that practice, we'll be in fine shape and excellent shape to be applying the Pythagorean theorem. So of course, here we go. Let me head back up to example 1. Now in example 1, I always get that wrong. In example 1, x is a leg. Okay, I know that because your right angle is here. So the side across from it is your hypotenuse side. This is your C side, right? So when plugging into a squared plus b squared equals c squared, we know that a or b is 7 squared. And this is going to be my b side. So x squared goes here. And then 18.4 goes here and gets squared. Okay, so we know 7 squared is 49. And we'll leave this x squared because we don't know it yet, right? But now we've got 18.4 squared. Okay, so 338.56. Start by subtracting 49 on both sides. So we get x squared equals 289.56 5, 6. Ah, too bad 289 wasn't alone, right? Because when that would be a perfect square. Take the square root of both sides. So square root, so second and x squared is your square root. If you just want the answer and you don't want to type in the thing you already have from the last problem, just press second and negative. It gives you your answer under there. So what I've got there right now under the radical is 289.56. Okay, so it's kind of neat. Just an easier, quicker way to get that. Taking the square root of both sides, I get x equals, and again, this should be plus and minus 17.01646262. Irrational. But because we know we can't have a negative length of a side, it's really just 17.016. Let's just stop here and call it 5. There's your length of your side. Again, this one, what's missing? What do we want to find? The length of the leash. This is an old Algebra 1 Regents question back when we had trig in Algebra 1. What we do here is a squared plus b squared equals c squared again. This time you know that the missing value is across from the right angle. So here is your hypotenuse. And that means that a is 5, b is 7, and c is your x. And each of those is squared. So 25 plus 49 equals x squared. And so what's this, 74? And when you take the square root of both sides, you think about whether or not, first of all, you don't keep the negative. And second of all, you think about whether or not 74 is evenly divisible by any perfect squares, of which it is not. And after that, let's see, we're done, right? I don't need to turn that into a radical unless I'm told, oh, to the nearest tenth. All right, so second, I like keeping radicals. I think they're much better, but nearest tenth, huh? So 8.6. 8.6 feet is the length of the leash. Now, just real quick, 8.6 is bigger than both 5 and 7. Yes, that's supposed to be the longest side. So yes, that is a correct answer. All right. So like I said, very rarely do we have the integers. So try to keep these in mind. I really do suggest memorizing them. I know that that's not everybody's favorite thing to have to memorize something, but you're going to see them so frequently and it cuts down on the amount of work you have to do so much that it really is kind of worth considering taking your time to memorize those, right? So 3, 4, 5, a 5, 12, 13, and 8, 15, 17. Those three really are the ones we see most. 7, 24, 25, and a 9, 40, 41. I've almost never seen a 9, 40, 41, but it's a possibility. I mean, there are an infinite number of these possibilities, but again, do we see those often? No. These are the ones we see most often. And really, I would say these are the ones we see most often. Okay. Where does this come in handy? Well, if I look at these, rather than having to plug into the Pythagorean theorem, I can spot a 3, 4, 5 right triangle and I can know my answer. So again, the 5 at the end has to be the hypotenuse. So 3 and 4 have to be legs, and in this case they are, which means that x equals 5. Okay. Here, this is a 5, 12, 13, because 13 is the hypotenuse, 12 is one of the legs. That leaves this leg has to be 5. Okay. Here, we have a 14 something 50. So let's consider, could those all evenly divide by something? Well, let's see. 14 is evenly divisible by 2, and I get 7. 50 is evenly divisible by 2, and I get 25. So this side, this is a 7, 24, 25 right triangle, which means that if I want this side in my head, I just multiply 24 times 2, which is 48. So again, rather than having to plug into the Pythagorean theorem, I have this option. Now, could I have Pythagorean theoremed this? Yes. So 50 squared is 2,500. Now subtract 14 squared from that, and this is what's left over, right? Because 14 squared is right here. Take the square root of that. So second and negative gives me that answer in there, and boom, because this is a perfect square. Now, did I know that was a perfect square before today? No. I wouldn't have recognized that perfect square off the top of my head. Okay. But again, I have this option of A, graphing calculator, B, knowing a 7, 24, 25 right triangle and its multiples. So when I'm seeing a right triangle that's all sides divisible by the same thing, I'm kind of thinking, let me see if that's one of these: a 3, 4, 5, a 5, 12, 13, an 8, an 8, 15, 17, a 7, 24, 25, or a 9, 40, 41. Okay, so I'm kind of thinking that route first, and then I go to the Pythagorean theorem route. Most of the stuff is review, of course, from stuff you've already done. So when you go to do that on your homework tonight, hopefully that geometry stuff all comes screaming back to you, right? Okay, the first foray into trig together. We got this, guys. I'll be seeing you. Have fun.